The airframe shuddered like a car hitting railroad ties. Mach .98 on the indicator, engines screaming at full military power, and the YF-102 just stopped accelerating. Not a gradual tapering off, a wall. The nose pitched and bucked, the controls went mushy, and the test pilot, Dick Johnson, Convair's best, sat in a $100 million airplane that could not do the one thing it existed to do. Somewhere in Moscow, Soviet air defense planners had already done the math. The Americans had bet their entire interceptor program on a single delta-wing airframe meant to sprint past Mach 1, climb to 50,000 feet, and kill incoming bombers with radar-guided missiles before they reached Chicago or Seattle. If that airplane couldn't break the sound barrier, the Continental Defense Plan had a hole in it the size of Lake Michigan. And by late 1953, every indication said the hole was real. So how did the worst aerodynamic failure in Air Force history become one of the longest-serving interceptors ever built? If that question hooks you, hit subscribe and drop your guess in the comments. I want to know how many of you already know the fix. Hit the like button too, because more people need to hear this one. The YF-102 started life as the backbone of Project 1954, the Air Force's grand scheme to automate air defense. Ground radars would detect Soviet bombers. Sage computers, room-sized machines fed by telephone lines, would calculate intercept courses. And the 102 would fly those courses on autopilot, launch its Falcon missiles, and turn for home. The pilot functioned more as a systems monitor than a fighter jockey. The whole concept required speed. Without supersonic dash capability, the geometry of interception fell apart. A subsonic interceptor couldn't close the angles on a jet bomber crossing the DEW line at 45,000 feet. Convair knew this. They'd built the Delta Wing XF-92 back in 1948, the first American Delta to fly. They understood swept planforms. They understood supersonic theory, or thought they did. The YF-102 used a straight-sided fuselage mated to a 60-degree delta wing, and wind tunnel data said it should punch through Mach 1 without afterburner. Wind tunnel data lied. The prototype flew on October 24, 1953 out of Edwards. Within a few flights, the numbers told a brutal story. Drag rose so violently near Mach 1 that no engine in the American inventory could push the airframe through. The transonic drag spike exceeded predictions by roughly 30%. Convair had spent 4 years, and the Air Force had committed over $1 billion in 1950s money, roughly $12 billion today, to an interceptor slower than the F-86 Sabre already parked on the flight line. A dayfighter from 1947 could outrun the airplane designed to save the continent. The program should have died right there. The paperwork for cancellation crossed 3 desks at Wright-Patterson, Fort Worth, Texas, 1953. Inside Convair's Plant 4, the fluorescent lights never shut off. Engineers worked double shifts redesigning an airplane that had already rolled off the production jigs, 23 airframes in various stages of assembly, every one of them subsonic. The smell of riveted aluminum and hydraulic fluid hung in the air like a permanent weather system, and the mood matched. Convair had staked the company on delta wings. Not hedged, not diversified, staked. The B-58 Hustler bomber, the F-102 interceptor, a dozen paper studies for delta wing fighters and transports. If the delta concept collapsed, Convair's entire product line collapsed with it. Company President J.T. McNarney, a retired 4-star general who understood Pentagon politics better than aerodynamics, told his board the fix would come. He did not say where from. 600 miles east, the fix already existed. It sat in a stack of NACA technical notes on the desk of a 32-year-old researcher at Langley who talked to almost nobody. Richard Whitcomb had spent 3 years staring at wind tunnel data that made no sense until it suddenly did. The drag rise near Mach 1 had nothing to do with wing shape alone. It depended on the total cross-sectional area of the entire aircraft. Wings, fuselage, engine nacelles, everything, plotted along the longitudinal axis. If that plot showed sudden jumps or bulges, the airflow choked, transonic drag spiked, the airplane hit a wall. The British had stumbled toward a similar insight a few years earlier. At the Royal Aircraft Establishment in Farnborough, aerodynamicists working on the Swift fighter noticed that fuselage shaping affected transonic drag far more than wing sweep alone. But they never formalized the principle into a usable design rule, and the Swift program lurched from crisis to crisis until the RAF pulled it from frontline service after barely 2 years. Back at Langley, Whitcomb did formalize it. His area rule said, the cross-sectional area distribution of a supersonic airplane should follow a smooth curve, roughly the shape of a Sears Hawk body, the theoretical minimum drag form for a given volume. Where the wings added area, the fuselage had to subtract it, pinch the waist, indent the fuselage right where the wing root thickened it. One NACA memo described the resulting shape as resembling a Coca-Cola bottle, and the name stuck forever. Whitcomb presented his findings to Convair in September 1952, a full year before the YF-102's first flight. Convair's own aerodynamicists reviewed the data. They acknowledged the theory looked sound. Then, they built the airplane with a straight-sided fuselage anyway, because redesigning the production tooling would have delayed delivery by 18 months and risked losing the contract to Northrop. That decision cost the Air Force a year, roughly $400 million in redesign work, and very nearly the entire Continental Air Defense Interceptor program. The original NACA report on area rule, Technical Note 3381, uses the phrase substantial reduction in transonic drag to describe what Whitcomb's shaping achieved. Substantial undersells it by a factor of about 10. Wind tunnel tests showed drag reductions near Mach 1 of roughly 25%. Convair had the answer in hand and chose the schedule over the physics. The schedule lost. December 21, 1954, Edwards Air Force Base. Morning sun threw long shadows across the dry lakebed, and the two airplanes sat nose to tail on the ramp, like a before and after photograph of the same idea. Same Pratt & Whitney J57 engine, same 60-degree delta wing, same vertical tail, same basic landing gear geometry. You could walk from one to the other in 15 seconds, but your eyes told you something had changed in a way that went beyond cosmetics. The original YF-102 had a fuselage shaped like a cigar tube, constant cross-section from just aft of the radome to the engine bay. Clean lines, symmetrical, wrong. The redesigned airframe, now designated YF-102A, looked like someone had grabbed it by the middle and squeezed. The fuselage narrowed dramatically where the wings met it, then flared again behind the trailing edge into bulged fairings that housed nothing but air. 11 feet longer overall. The canopy sat farther forward, the nose stretched into a sharper point, and the whole machine carried an almost biological curve to it, something closer to a fish than an airplane. Convair's engineers had done more than pinch the waist. They'd reshaped every external surface to match Whitcomb's area distribution curve. The intake geometry changed. The aft fuselage gained those strange bulges to compensate for the area lost where the jet pipe narrowed. Internal weapons bay doors got thinner fairings. Even the canopy profile shifted to keep the cross-sectional plot smooth. 14,000 engineering changes total. Same engine, same thrust, same wing, and according to the slide rules, roughly 25% less transonic drag. The slide rules had been wrong before. Test pilot Pete Everest, a man who'd already pushed the X-2 past Mach 2.6 and did not impress easily, strapped into the YF-102A that morning. He lit the afterburner on the climb-out over the Mojave. The Mach indicator crept through 0.95, past 0.98, where the original airframe had hit its wall, through 0.99. The needle kept moving. Mach 1.22. Level flight, standard altitude, no dive to cheat the numbers. The airframe that couldn't break the barrier 3 months earlier now cruised past it, like the barrier had packed up and left. Same engine, same wing, different fuselage shape, that's all. The air didn't know it was supposed to be the same airplane, and it didn't care about Convair's production schedule or the Pentagon's budget fights. It only knew the body moving through it had changed from a blunt obstruction to something it could flow around without choking. Whitcomb won the Collier Trophy that year, aviation's highest honor. The citation praised his contribution to aeronautical science. It did not mention that the contribution had been available 18 months before anyone at Convair bothered to use it. What do you do with an airplane the entire Pentagon had written off 6 months earlier? You build 875 of them. Convair's Fort Worth line ran hot from 1955 through 1958, stamping out production F-102As at a rate that made the bean counters at Air Materiel Command nervous for entirely new reasons. Not because the airplane didn't work, but because the Air Force couldn't train pilots fast enough to fill the cockpits. 26 Air Defense Command squadrons stood up across the continental United States, from Duluth to Miami, Suffolk County to McCord Field, each one plugged directly into the SAGE network, the ground-based computers feeding intercept vectors straight to the aircraft's autopilot through a data link that, for 1956, bordered on science fiction. The mission profile ran like this. Soviet bombers crossed the Arctic. DEW line radars acquire them somewhere over northern Canada. SAGE computes the intercept geometry, bearing, altitude, closure rate, and transmits it to a 102 sitting alert with its pilot strapped in and both engines idling. The pilot takes off. The autopilot flies the intercept, and at the merge, the fire control system launches a salvo of AIM-4 Falcon missiles. Or, if the bomber stream looked thick enough to justify it, a single MB-1 Genie, unguided nuclear rocket carrying a 1.5 kiloton warhead, 1.5 kilotons, roughly a tenth of Hiroshima, fired from an airplane, at an airplane. The Air Force tested the Genie exactly once with a live warhead, Operation Plum Bob, Shot John, July 19, 1957. An F-89 Scorpion fired the rocket at 18,700 feet over 5 volunteers standing hatless at ground zero in the Nevada desert. All 5 survived. The Air Force called the test a success and never repeated it, which tells you something about how confident they felt about a second data point. Former ADC pilot Colonel Robert Robinson described sitting nuclear alert in a 102 at Perrin Air Force Base as the strangest combination of boredom and existential dread he'd ever experienced. You sat in a ready room playing cards, he said, knowing that if the klaxon sounded, you had 5 minutes to be airborne carrying a weapon that would vaporize everything within a quarter-mile radius of the detonation point, including, if your escape maneuver went wrong, you. The 102 couldn't dogfight. Pilots joked that it turned like a freight train and bled energy in any bank steeper than 45 degrees. The Delta Wing gave it beautiful high-altitude straight-line performance and absolutely punishing low-speed handling characteristics. Landing speeds north of 170 knots, no leading-edge devices. Approach angle of attack so high, the pilot couldn't see the runway over the nose. None of that mattered. The airplane existed to do one thing: sprint to altitude, point at a bomber, and kill it before it reached Omaha. For that mission, in that era, against that threat, the Coke bottle fuselage and the SAGE data link and the Genie rocket made the F-102 exactly sufficient. Nobody called it elegant or loved flying it, but it did the job. Convair avoided bankruptcy by about 90 days. The production contract for 875 airframes landed in March 1955, 4 months after Everest's supersonic flight. The company's own financial records show they carried less than 3 months of operating capital when the money arrived. Whitcomb's waste didn't just save an airplane. It saved a company, a defense strategy, roughly 30,000 jobs in North Texas, and arguably the entire continental air defense concept the Eisenhower administration had staked its budget on. Every airplane I design from now on will look like it swallowed a snake. That's how one Convair engineer described the post-Whitcomb world to a colleague in 1956. He wasn't wrong. Look at what followed. The F-105 Thunder Chief, Coke bottle fuselage, the F-106 Delta Dart, refined Wasp waste, Convair's own sequel, the B-58 Hustler, the F-4 Phantom, every Century Series fighter, every supersonic bomber, every Mach 2 interceptor the free world fielded for the next 3 decades carried Whitcomb's area distribution in its bones. The Soviets adopted it too. The MiG-21's fuselage narrows exactly where the delta route thickens. They read the same physics. Whitcomb never flew, never wore a uniform. He rode a bicycle to work at Langley for 40 years, ate lunch alone, and kept refining the same obsession: how air moves around shapes. He developed the supercritical wing in the 1960s, which now hangs under every commercial airliner you've ever boarded. NASA gave him its Distinguished Service Medal. He died in 2009 at 88 in a small house in Hampton, Virginia, and the obituaries ran about 4 paragraphs each. The Soviets, meanwhile, spent 2 decades building an air defense network specifically designed to kill the bombers the F-102 had been built to stop: SA-2s, SA-3s, MiG-21 interceptors, ground-controlled intercept radars, all of it optimized against high-altitude bomber streams crossing the Arctic. By 1962, the threat had shifted to ICBMs. The bomber stream never came. The Soviets had built the most elaborate anti-bomber defense in history against an attack concept the Americans had already abandoned. Convair merged into General Dynamics in 1961. General Dynamics sold the Fort Worth plant to Lockheed Martin in 1993. The building where 23 straight fuselage F-102s sat waiting for a fix that already existed on a desk in Virginia. That building makes F-35s now.